Here you see two things known as phase diagrams. One of these diagrams is going to be for carbon dioxide, the other is for water. Now there's some features that are common between these, but there's also going to be some important differences. So actually let's take a look at them and see exactly what's what and what things are happening when. Now, carbon dioxide, we have probably interacted with solid carbon dioxide in our lives and liquid carbon dioxide, gas phase carbon dioxide too. If you've breathed out recently, you've had carbon dioxide nearby. If you don't breathe anymore, please pause the video and go see a doctor. Now, with the solid phase carbon dioxide, we're talking about dry ice. And if you go down to Publix, you can find a chunk of dry ice in most of those sitting in a cooler, and they're at a really cold temperature. Cold enough that it'll give you frostbite if you just grab a chunk of it without any protection. It is solid at negative 78 degrees under atmospheric pressure. And of course, that's what we're used to interacting with, is atmospheric pressure. So what we're used to seeing is what's happening right along this line, if my hand is steady enough. At very cold temperatures, it's a solid. Then it turns directly into a gas at higher temperatures. Now, if we get to a higher pressure, we would actually be able to have liquid carbon dioxide around. For that, we'd have to be at about 5 times, well, a bit more than 5 times normal atmospheric pressure. And then we'd actually be able to melt the carbon dioxide and see the liquid carbon dioxide. And then we could have the liquid carbon dioxide boil into gas phase carbon dioxide. Now, whenever you're trying to remember which regions are which, you can think through things kind of like that. Just say, all right, if I'm at a certain pressure, what happens as I come across? Now, if you were up here, you'd say, well, at very cold temperatures, I'm a solid. As I heat up, I'm going to be a liquid. As I heat up more, I'm going to be a gas. So that's a quick way to remember which region you're actually talking about. And of course, as long as we have our terminology memorized, we know that going from solid to liquid, that phase transition is melting or freezing, and is our heat of fusion. As we go from vaporization, condensation, with liquid to gas, that's going to be enthalpy of vaporization, and we call that either boiling or condensation, or vaporization and condensation, we should say. And we can have our sublimation deposition down here, and that would be going directly from solid to gas phase. Okay, now all of that's going to be happening for carbon dioxide, and of course the same thing should be happening for water. Now let's come back to carbon dioxide for another minute, though, just to finish highlighting a couple points, and then we'll compare and contrast to water. So you see here we have a spot where at a certain temperature and pressure we can have all 3 states of matter simultaneously. And I don't just mean that, I've got some water with ice cubes in it, and then I'm blowing across it, which means that technically I've made water that's gas phase with my breath. That's not a stable condition. I have to do something constantly to make that happen. At that triple point, we have all 3 states of matter, and they remain stable like that. So you can have gas, liquid, and solid all coexisting, and you're not having it be a transient thing, as long as you maintain that temperature and pressure. Now, there's another important point on there, and that's the critical point. Above the critical point, we actually have the supercritical fluid. I'm just going to call it SCF, supercritical fluid. That's not a proper term, but I just wanted to have it marked for you. Now, you can see that 73 atmospheres, that's high pressure, but it's not an unrealistic pressure. I mean, with normal equipment, you can picture us getting 73 atmospheres in just, a high pressure cylinder of gas. At 31 degrees Celsius, that's not very hot. We don't have to heat it up a whole lot to get carbon dioxide above the critical point. Well, above the critical point, supercritical fluid will act like both a gas and a liquid. So it's neither one, but it's a little bit of both. You can dissolve things in it like you would dissolve with a liquid. Now, that means carbon dioxide can be used for very, very evil purposes. It can diffuse through solids just like a gas or a liquid would. More like a gas, probably. But it can also dissolve some solids like caffeine and have it remain dissolved in this supercritical fluid. That's how they get the caffeine out of, well, one of the ways they get caffeine out of coffee beans. Now the other neat thing about it is you don't have boiling when you go from supercritical fluid to gas. It's just that finally they have a little bit of elbow room between the molecules and they start acting more like a gas again. But they never actually boiled. So that means that when you start to gradually release the pressure at 31 degrees Celsius, or I guess 35 degrees Celsius or something, you're going to come from supercritical fluid into the gas phase without boiling. You just finally gave them enough elbow room that they start acting like a gas again. The carbon dioxide is crystallizing, the caffeine is crystallizing out in the process, so you get a big old pile of caffeine crystals sitting over on the side, and you have your decaffeinated coffee beans remaining behind. So it's a pretty evil process. Now, if you were trying to do something like etch a microchip and etch all the little circuits onto the microchip, and you wanted to dissolve away the other stuff that you just etched off, but you don't really want to have it boil and suddenly blast all those tiny little circuits off of the board in the vigorous boiling process. What do? You dissolve it off using a supercritical fluid, and you gradually release the pressure while maintaining temperature, and sure enough, you dodge the boiling issue. You don't end up creating the vigorous action of boiling, and you don't shake off those little features. So that's one of the neat things you can do with supercritical fluid. A good one and an evil one. Now, water can also be a supercritical fluid, but boy, do you have to get to a high temperature and pressure for that to happen. Now, we see a couple of key features here for water, and they're the things that we're used to seeing. Water boils at 100 degrees Celsius at atmospheric pressure of 1. And then it freezes at 0 degrees Celsius when pressure is 1 atmosphere. It's a solid, then it's a liquid, then it's a gas as you heat it up. We don't really see the critical point. We don't really see the triple point under our normal conditions because you have to kind of get to pretty exotic conditions for any of those to happen. Notice how low you have to get atmospheric pressure and your pressure in order to actually get to the triple point. So we're not likely to see that unless we're really in a vacuum chamber in a lab. Critical point, again, we'd have to be at really high pressures and we'd have to be at pretty hot temperatures in order to get there. But notice the other weird feature between these. Here, carbon dioxide has like a positive slope. So if I stay at the exact same temperature, just try to draw a totally straight line, not totally straight, but good enough, you'll see that as we go to a higher pressure, we're going to go from liquid to solid. And that kind of makes sense to us. As we put more pressure on a liquid, it's finally going to get so close that the intermolecular forces grab hold of its neighboring molecule and turn it into a solid. Now, water does something a little bit weird there. If we pick -1 degree Celsius, just to help guide the eye, and we're raising our pressure. Notice when we start at atmospheric pressure, sure, -1 degree will definitely be a solid. But it does something a little bit strange. As you increase the pressure, it's actually going to have its phase change go the other direction. It's actually going to turn from solid back to liquid. Now we do use this to our advantage when we're ice skating. By putting all of our weight onto the fine edge of the blade of the ice skate, what you're actually doing is you're putting enough pressure that while it's staying the same temperature, you're actually crossing this threshold going this direction. You go from solid to liquid phase. In the process, you end up having a nice lubricating layer of water at the surface of the solid, and now the blade of the ice skate can just slide right across it with low friction. So that's one of the neat tricks that we use there. Now I'm not going to go into all the details of why the slope goes like that and bring that back down to the microscopic level, but it does get raised in enough other contexts that I wanted us to see that here on the phase change diagram. So if you have this backward slope, then you can have that condition where by increasing pressure you actually go back into the liquid phase. Normally increasing pressure, you're going to force it to go into the solid phase. It's one of the very, very, very many reasons that water is weird.